about holographic correlators.
So let me then share my screen. It worked a second ago. So fantastic. So can you see my slides?
Yeah.
Perfect. Thank you very much.
But let's wait 20 seconds. Let's start.
I can wait 20 seconds, yes.
Okay, it's okay. It's good. No, it's 11 sharp. Good.
I can wait as long as you want.
Go on. Now it's good.
So I feel a little bit out of place because I will not be talking about integrability. I will not be talking about a gauge theory, and I will not be talking about strings either. But hopefully you find that this interesting. So I would like to start by thanking the organizers for giving me the opportunity to present my work here. So I will be talking about 6D 2.0 correlators and quantum Mtheory. I was expecting a quite wide audience, so I will try to be pedagogical, but feel free to stop me with any questions if you have any questions. And this work, this talk is based on work in collaboration with Shai Chester, Himanshu Raj, and Shinan Shou. So this talk will be about conformal field theory techniques to study scattering amplitudes in theories of gravity, and in particular, string and M-theory. So the target for today will be the 4-point graviton amplitude in M-theory, or more precisely, the 4-point supergraviton amplitude in M-theory. An scattering amplitude is basically the probability that if you have two particles scattering with momenta P1 and P2, they produce other two particles with momenta P3 and P4. And in the particular case that we are interested, which is M-theory, this amplitude will depend on a length, which is the 11-dimensional Planck length, and three Mandelstam variables, S, T, and U, which are some combinations like P1 plus P2 squared, etc. Now, it is fair to say that we don't have a non-perturbative understanding of what M-theory is. However, for the purposes of this talk, will be enough to focus on perturbative M-theory. And perturbatively, M-theory is simply 11-dimensional supergravity, so in a low energy expansion, is 11-dimensional supergravity plus an infinite tower of higher derivative corrections. So the effective action looks something like this. The first term is the term that corresponds to 11-dimensional supergravity. It's the same as the Einstein-Hilbert action, but you need to complete it, of course, by using supersymmetry. And then we have a whole tower of higher derivatives operator. Now, higher derivative terms in this expansion carry powers of L, which is the 11-dimensional Planck length. It is known, for instance, that we have a term that goes like R to the 4 and D6 R to the 4, and the coefficient of these two terms is actually known. And also, we know that the terms D2 R to the 4 and D4 R to the 4 are actually absent. On the other hand, starting from the term D8 R to the 4 and higher order terms, all these coefficients are unknown. So already this coefficient here, we don't know what it is. Instead of studying an effective action, or one way to study an effective action, is by looking at an on-shell quantity, which in this case is the 11-dimensional 4-point gravity amplitude in a momentum expansion that correspond to this expansion in powers of L of the effective action. Now, in flat space, this amplitude takes the following form. So it depends on the momenta and the polarization vectors of the gravitons undergoing the scattering, and all the dependence on the polarization is inside this universal factor k hat, which is known, but I am not writing it down. Then we have a series expansion in powers of the Mandelstam variables. So for instance, here we have 1 over STU, 1, STU, etc. And it turns out that because of what I said before, the coefficients of higher polynomials in ST and U are actually not known. In addition to this polynomial expansion, we have loop terms that can be, sorry about that, that can be determined from these three-level terms that are some complicated non-analytic functions of the Mandelstam variables ST and U. And the first term, that was the only term computed explicitly before our work, corresponds to the loop supergravity term. It goes like L to the 9, so it's between these two in an L expansion, and it is given by the 11-dimensional box function, which is some complicated function of ST and U. So the aim for this talk, what we want to do, is we want to extend these results to curve space-time. Okay, so this is what we are going to try to do. Now, in order to do that, we need to consider a completely different approach to this problem. And this approach will be using the DCST duality. But in this case, I will not use the usual DCST duality relating a string theory on EDS 5 × 5 to n equals 4 super Yang-Mills, but rather we use the DCST duality relating Mtheory on EDS 7 × 4 to a 6-dimensional superconformal field theory living in the boundary of this EDS 7 space. This theory is the supersymmetric, the maximally supersymmetric theory in 6 dimensions, and it is the so-called 6-dimensional 2,0 theory with central charge C. Now, it turns out, so it is known that M-theory doesn't have a dimensionless coupling constant. However, as soon as you put M-theory on a curved manifold, we have a length, which now is given by the radius of EDS, and with the 11-dimensional Planck length, we can form this dimensionless ratio. And this duality also gives us the dictionary between the radius, the 11-dimensional Planck length L, and the central charge of the CFT C. Notice from this dictionary that a momentum expansion, which corresponds to an expansion in powers of L, maps to a expansion in 1 over C. Please do let me know if there are questions because I cannot see the chat. So someone do let me know and stop me if you have any questions. Now, the DCST duality also tells us a bit more. So it tells us how do we need to think about M-theory amplitudes on EDS 7 × 4. Now, when you want to define scattering amplitudes, it is very important that you define asymptotic states. And this is not a very easy thing to do in EDS because EDS is like a box. But the way to define them is that we need to map them to correlators of local operators in the boundary 6D 2,0 theory. Okay? So we have this very nice picture here. So the amplitude that we want to compute corresponds to some local correlator of local operators, in this case, a 4-point function, in this 6D 2,0 theory. Now, also, we want to consider the scattering of gravitons. So we need to say which operators corresponds to gravitons. Now, in this 6D 2,0 theory, there is a tower of half BPS operators of dimension 2K, such that O2 corresponds to the graviton on EDS. On the other hand, because of the S4, there is a tower of Kaluza-Klein modes, and this tower of Kaluza-Klein modes maps to these operators OK for K equals 3, 4, 5, etc. So ideally, what we want to compute is OK1, OK2, OK3, OK4 in a 1/C expansion. Now, maybe for the younger audience, so something that makes this computation a bit hard is that this 6D2,0 theory is not a Lagrangian theory. So you don't have a Lagrangian. In particular, you don't have techniques like localization or integrability. And also all this wealth of perturbative data at weak coupling that we have for n=4, we don't have it for this theory. So somehow we need to kind of bypass the use of any Lagrangian because we don't have one. Now we want, let me tell you a little bit about the kinematics of the problem. So the theory is the 6D2,0, and this is the maximally supersymmetric theory in 6 dimensions, and it has a superconformal algebra which is OSP 8*/4. That's just a name, it doesn't matter. But what is important about this algebra is that it has a bosonic subalgebra, which is given by SO6,2, which is the conformal algebra in 6 dimensions. And then we also have an R-symmetry group, which is SO5 in this case. It's the analog of the SO6, like in n=4. There is a bunch of half BPS operators, and half BPS operators transform in the symmetric traceless representation of SO5. So they are operators like this, and they have k indices where each one of these indices runs from 1 to 5, transforms each one in the fundamental of this SO5. Now, rather than carrying, and each of them, is a local operator, so it's evaluated at a point in this 6-dimensional space. Now, rather than carrying these k indices around, which is a bit cumbersome, we will introduce for each operator a null vector y, 5-dimensional null vector y, such that y² is equal to 0, and we will contract all these k indices with k of this, k times this vector y. So we finally have these operators, OK, which are a function of a point in 6 dimensions and a null vector, 5-dimensional null vector. And what we are going to do, we are just going to consider the 4-point function of these guys, okay? Now, as a consequence of conformal symmetry, it turns out that if we extract a prefactor here, and this is true for K1, K2, K3, K4, all different, but just for simplicity, I am setting all of them equal. And because of conformal symmetry, if you extract them, if you extract this prefactor, then it turns out that the correlator is not a function of x1, x2, x3, x4, but rather these two invariant cross ratios denoted by u and v, where this x12 square is x1 minus x2 square and so on. And exactly the same happens with the R-symmetry part. If you extract this prefactor, y1 dot y2, etc., everything is a function of sigma and tau, which are these two cross ratios formed, are these R-symmetry cross ratios formed with the y's. It is easy to see because the amount of y vectors is fixed, that this is actually a polynomial in the variables sigma and tau, okay? Now we want to compute this correlator in a 1/C expansion. Now the 0th order is somewhat trivial, no one talks about it, and it's just a disconnected contribution. The first, the leading non-trivial order, is what is called the correlator in the supergravity approximation. And it's the piece of the correlator that goes like 1/C, the central charge. So in the next 10 minutes or so, or 5 minutes, we will see how to compute this correlator, this leading 1/C piece. Now, there is a standard recipe on how to do this, first introduced, I guess, in the most cited paper by Ed Witten. So what one has to do is you take this 11-dimensional supergravity effective action and you do a Kaluza-Klein reduction on S4, okay? This gives you an effective action on ADS, and from that effective action, you can read off the cubic and the quartic vertices. Once you have read off these cubic and quartic vertices, you can write down all exchange and contact Witten diagrams. And then you have to compute them, okay? So this is in principle a recipe. It should, I guess, work. However, in practice, this is an impossible thing to do. It is almost impossible with the things we know to compute this effective action. It has been done for the case of ADS 5 × S5, and it takes more than 15 pages. And even if you were able to do that, the amount of Witten diagrams would be huge. But even if you were able to write them down, you wouldn't be able to compute them, okay? So this is actually not possible in practice. So let's try to understand how we can fix the answer by using consistency conditions instead of a brute force computation. And the right language to do this is Mellin space. So instead of talking about the correlator, which is a function of two cross ratios, we will move to a function of three variables, st and u, which are much closer to the Mandelstam variables, but with one constraint, such that s plus t plus u is equal to a constant, which, okay, is ak in the case in which all ki's are equal to k. So this function is secretly a function of two variables only. And the relation between the correlator and this function m is given by this integral transform, okay? So this is a, sorry, are there any questions? Okay. So the relation between the correlator and this Mellin amplitude is given by this integral transform. So here this gamma is a standard prefactor. It's just a product of gamma functions. And it turns out that this one is the m, this one is the function that we need to interpret as the Mtheory amplitude on ADS 7 × S4. It is in one-to-one correspondence with the full correlator, but it's a function that has much nicer properties, and it behaves much more like an amplitude. In particular, it is a meromorphic function. Meromorphic means that it's basically analytic, except in a few points. It satisfies nice properties under crossing symmetry. Then the exchange of operators, for instance, like the one in this diagram here, lead to simple poles. Let's say if you have an S-channel exchange, you will have some series of poles in the S-channel with some well-defined residues at these poles. And in addition, as a third condition, it satisfies what we call the superconformal word identities. Remember that I told you the fact that we can write down the correlator like this is a consequence of the bosonic subgroup of this supergroup here. In addition, there is a fermionic part as well, and this fermionic part imposes a relation that just looks like some operator acting on m equals 0. Okay, it's complicated, but you can just write it down in Mathematica. So now, an idea which was first used by Rastelli and Shaw is that rather than using the effective action, we can try to use 1 plus 2 plus 3 and see how much that fixes the answer. Now, it turns out that in the case at hand, which is ADS 7 × S4, with this method, we can produce results case by case, but this is still very inefficient, and it is hard to see any structure. And in order to proceed, we need a new idea. And this new idea is the concept of maximally R-symmetry violating amplitudes. And the idea of these MRV amplitudes is the following. Remember that I told you that each operator in the correlator depends on a 6-dimensional point x and a null 5-dimensional vector y. What we are going to do now is we are going to choose a configuration where y1 and y3 are aligned, so that y1 dot y3 is equal to 0 because they are null. In terms of cross ratios, of R-symmetry cross ratios, sigma and tau, this means that sigma, we are setting it to 0, and tau, we are setting it to 1. And this special amplitude for sigma equals 0 and tau equals 1, we call it a MRV amplitude of S and T. So the beauty of this is that this suppresses all supergravity exchanges in the U channel because they are all proportional to y1 dot y3, and the amplitude simplifies drastically. So just to show you a couple of
5
examples.
minutes now.
Yes, sorry.
5 minutes now.
Okay, thank you. So just to give you an example, so this is the stress tensor multiplet 4-point function for a DS7 cross S4. This is the simplest 4-point function, is the O2, 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 O2. And you see that although it is the simplest, it is quite horrible. So it has a series of poles here in S, T, and U, and it has some horrific numerator, which is this polynomial on S and T, sigma and tau. However, if we set sigma to 0 and tau to 1, we obtain this much simpler expression in the MRV limit. Now, in particular, notice two things about this. So this has no poles in the U channel for what I just explained before, but in addition, it contains a double zero in this variable U. This can be understood as some low twist double trace long operators that decouple in this specific limit. But the point is that it is general. It happens for all amplitudes, for all K1, K2, K3, K4, and it is highly non-trivial at the level of exchange Witten diagrams. So if you come to these Witten diagrams and you try to understand this double zero, it is actually a pretty strong condition. And it is so non-trivial that it gives a set of relations for the cubic couplings, and it fixes all couplings in terms of the scalar, in terms of known cubic couplings. And as a matter of fact, we can actually write down the general MRV amplitude for all K1, K2, K3, K4. And now it comes something even nicer. We can use our symmetry to restore the full sigma and tau dependence, and we can write down the full answer for all three-level amplitudes, all supergravity amplitudes for all K1, K2, K3, K4 in a DS7 cross S4. So this is just a sum over single poles with very specific residues, which we give, and it's a compact and explicit expression for all supergravity amplitudes. Let me press, so I think I will need 3 more minutes if that's okay. So let's now try to consider higher 1/c terms. So we just computed this supergravity result. It turns out that the next term corresponds to the quartic vertex R to the 4, and it goes like 1/c to the 5/3. And in Meline space, this solution simply corresponds to a polynomial. And again, this polynomial is fixed by consistency conditions. This is fantastic, and it allows us to fix all 3 correlators, this one, as I just shown before, and this one, which is much simpler. Now, we can ask what happens with loops, and in particular, this the leading term that goes like 1/c squared. Now, it turns out that the loops actually follow from trees. And in order to understand that, there is a very nice fact. And it's the fact that when you are in Minkowski space, not in Euclidean space, but in Minkowski space, you can consider a very interesting limit where the distance between two operators is 0, but is 0 not because the operators are together, but because one operator is in the null cone, in the like cone of the other one. And as operators become null separated, the correlator develops singularities. And these singularities are very interesting because of two things. First, because at a given order in 1/c, these singularities follow from the CFT data at previous orders. So that if you have solved the problem at previous order, you can write down these singularities at the next order. And second, because the whole correlator can be reconstructed from these singularities. And this in practice, what it allowed is to compute these loop correlators from the tree-level correlators. So let me just give you some results. So in a very precise sense, which I don't have much time to explain, each solution is actually the square of the solutions at previous order. And for instance, we can explicitly compute in Meline space this loop supergravity, that was the term that goes like 1/c squared. And this is just a metamorphic function with simultaneous poles, where these are complicated, but are actually completely explicit. So this is a quantum M-theory amplitude on ADS, and it's the first quantum correction for a non-Lagrangian theory. So this is the last slide before the conclusions. Now, with this, so putting together all the results I have shown, we have extended all the results that I shown you in flat space to actually ADS. Now, there is something with this ADS amplitude, there is something interesting that you can do. And you can recover the amplitude in flat space. In particular, you need to take the radius of ADS very large, rescaling ST and U accordingly. And if you do that from these results, first, we obtain a prefactor, which is this quadratic coefficient, and one can actually show that this prefactor exactly coincides with k hat, that was the prefactor that we had in the flat space amplitude. Then we have these results that are agree exactly with the results at tree level, and then, quite remarkably, exactly the 11-dimensional box integral. Notice that, in particular, this reproduces the one loop result in 11 dimensions, and we have recovered the 11-dimensional result from a 6-dimensional CFT computation. So we are really seeing that the bulk dual of the 2-0-6D theory has to be 11-dimensional. So let me conclude, and sorry for going extra time. So we have developed powerful tools to compute systematically, a string, but here I explain M-theory amplitudes in curved space. And we have computed all holographic correlators dual to ADS 3 amplitudes. And actually what I explained works for any maximally supersymmetric background. And this represents a milestone in the field of holographic correlators. People was trying to do that for a few decades. Then we also computed 1/c squared correlators in this non-Lagrangian theory. And what is interesting is that from this correlator, now you can extract a wealth of CFT data. So for instance, here, I just wrote down the 1/c expansion of the dimension of the leading twist operator with the spin 4. And we can compute these very precise numbers. Now, for the near future, the 62,0 theory gives a non-perturbative definition of M-theory, and we can try to use the bootstrap to answer questions about it. And a target question that we can answer if we compute, let's say with numerical bootstrap and with very high precision, this delta 4, is whether this term D8 R⁴ is present or not in the effective action. And this will be the first time that the bootstrap really teaches us something about M-theory. Thank you very much.
Thanks for the very nice talk. So questions now?
You computed a one loop diagram in 11 dimensions, and that I would expect to have a divergence. Why did the divergence didn't bother you?
Right. Yes. Well, so what I have to say, so there is a funny thing with this 11-dimensional. So when you compute the first comment is that when you compute the box in D dimensions, the box in D dimensions has a divergence, but the divergence comes in the form of a gamma function of minus D over 2. And if you set D to an even number, to an odd number, you can actually get a finite answer. So it is divergent, but in a way you get a finite answer. But the divergence here, we do see it, and we see because we get an ambiguity which is of the form of this vertex R to the 4. And this ambiguity arises when we reconstruct the full answer from the double discontinuity. So when we reconstruct that, we get ambiguities, and this ambiguity is proportional to like the divergences that you would get. But it's also true that if you get the box function in D dimensions and set D to 11, you seem to get a finite answer. But we do get it, and we get these ambiguities. So we will get some extra ambiguity, and this is the reason why here I chose this operator of dimension 4, sorry, of spin 4, because we do get an ambiguity, but this ambiguity is there only for spin 0 in this case. Oh, yeah, I can see. Is that okay? Does that answer the question?
Yeah, I think so.
Okay, so beautiful talk. So I did not, I somehow missed this maximally, these amplitudes that you introduced. They are very nice. So you say that in any theory, it's enough to stick to this configuration, y1 y3 equals 0, and then R charge is enough to rotate and get everything.
Right. So if I have one more minute, so let me be super precise, which I wasn't. So what happens, indeed, so what happens if you want to be more precise is that first you are able to compute precisely this MRV amplitude, which I compute here, sorry, which has some expression. And then from this MRV amplitude, you can reintroduce sigma and tau, because the point is that all the R symmetry polynomials survive in this limit. And because all R symmetry polynomials survive in this limit, you can recover the full amplitude, but more precisely, you can recover the full amplitude up to regular terms, up to contact terms. So in principle here, we could add contact terms, but what happens, we found a representation where you can use the superconformal word identities to show that for all cases, all contact terms are actually absent. So the precise statement is that from the MRV amplitudes, you can recover fully the polar part of the three-level amplitudes, and then with the superconformal word identities, you could in principle fix the contact terms, but we have managed to find a representation where this contact term is actually 0.
And how the first line that you wrote is very nice formula. If I were to compute it for k, for 4 k's equal but not 2, would it still be simple, or it will be complicated?
Yes, it's very simple. So it's relatively simple. We have a Mathematica program where you can set k1, k2, k3, k4 to whatever values, and in 1 second, you get the answer. So these zeros, the location, so it always, you have 2 zeros, and the location of the zeros depends on k. And also the number of poles depends on k. So for instance, for k equals 3, this will have poles at s equals 4, 6, 8, and 10. And the zeros will be shifted as well.
Okay. Let me just make one comment that if I understand correctly, this polarization y1 y3 equals 0 is the same as what Frank introduces in the simplest correlator that then leads to the octagon. Of course, it's a different regime because there k is the biggest parameter, so it's much bigger than squared lambda and so on in n equals 4, of course.
Right.
But it's the same analog simplification. I think it's the
That's
same. Maybe
very
Frank,
interesting. Yeah, there are actually 3 equivalent. So you can set y1 equals to y2 or y3 or y4. And with that, what you are doing, you are suppressing the exchange either in the U channel or S channel or T channel. So there are 3 equivalents. So it could be one of the other 2, but it could be equivalent.
Sorry, may I ask something?
Yes, of course.
So is it really different, this kind of configuration that you take, or does it add something more than the superconformal word identities in general?
Fantastic question. Fantastic question. And the answer is no. The answer is no. So notice that, however, it is way more efficient. So actually, in a case-by-case example, we can also fix the answer for all K1, K2, K3, and K4. However, from this, you cannot guess anything. But it is also true that if you were to use only the superconformal word identities, you also would fix all the couplings in terms of the scalar couplings. But you would have to do it like in a case-by-case, and with this, we can do it for all cases at once. Yeah, so indeed, it's a very good point, and it's just like a super efficient way of dealing with these superconformal word identities. But then there is this other bit, which we don't yet understand, and it's the fact that we can get a representation where you don't need to add these contact terms. Notice that in particular, this should imply that in the action that Frolov and Aryutunov found of this 20 pages action, there should be some field redefinition where you don't have quartic couplings at all. So there is some way of defining things where you only have cubic couplings. We don't need that, but it is quite remarkable that this exists.
Thank you.
Okay, let's move now to Silvio.
Can I ask a question? Sorry, can I ask another
One
question?
last question then.
Okay. So how does this MRV method generalize to higher points?
Right. That would be a big, yeah, that's beautiful. We don't know. The hope is that it tells us something. Of course, we don't expect it to fix the complete answer in that case. Very much like MHV amplitudes for higher points don't tell you what non-MHV amplitudes are.
Yes.
Yeah, but it would be very interesting to see if they tell us something about that.
Okay, I have some other question, but I guess I'll just ask in the discussion section. Thank you.
Thank you.
So let me unshare, I guess. Or maybe you can, sorry. Yeah. Thank you.